properties of metals. So people more and more study in details some exotic systems, exotic ordering, exotic structures, and exotic transition, and it seems that these two classes of strongly correlated systems both belong to the same category. Okay, this is all what I wanted to tell you about quantum phase transitions. And now let's go to the summary of the course. So what actually did we discuss in the course? Any questions, by the way? It seems to be unhappy. No? So what did we study? Of course, neither in 20 lectures or in 200 lectures it's impossible to discuss everything. Moreover, the choice of topics is a matter of taste or my scientific interests. This is clear that another person will probably have another selection of topics. But let's discuss the structure of what we have discussed in the course of many I may classify the topics, of course, in probably three big groups. Namely, we discussed many body effects in Bose systems, in Fermi systems, and in spin systems, which in fact are neither Fermi nor Bose. So in Fermi systems, we discussed the effects associated with the interaction. Well, first of all, we discussed the basic principles which are responsible for behavior of Fermi systems, namely Pauli principle, which actually stands behind the formation of Fermi surface, and all phenomena associated with the fact that fermions, the ground state of fermionic system, is given by the states in the field sphere. So all states inside sphere are filled in, and this is the ground state of fermionic system. And the surface of this sphere, and I will show you in one of the lectures that the real Fermi surfaces very seldom have anything in common with spherical shape. So all collective properties of fermionic system are one way or another one related to existence of the Fermi surface. So we discussed the effects of interaction. And come to very important concepts of quasi-particles. Defining another important concept, which is a lifetime of the quasi-particles, which is the same as excitations. So we discussed the single particle excitations in the Fermi system, which are electrons and holes. So electrons as excitations live above Fermi surface, and holes live below Fermi surface. And both quasi-particles are characterized by linear spectrum in the vicinity of Fermi surface. And moreover, the closer we are to the Fermi surface, the better quasi-particles are defined, because the lifetime of quasi-particles goes to infinity when we approach to the Fermi surface. We discussed a little bit two-particle excitations, because I mentioned the electron-hole pairs, which contribute to polarization of this Fermi system. But what has also been said about fermionic system is itinerant magnetism. In actually three ways. We discussed Pauli paramagnetism, Landau diamagnetism, and Stoner and principles of diamagnetism. So we discussed these three kinds of magnetism in itinerant system, and in addition to that, at the last part of the course, we discussed effects of Coulomb interaction, and disorder. So this is what is more or less has been discussed for the case of Fermi systems. Now let's come to Bose systems. While discussing the same kind of collective phenomena in Bose system, or many body effects which manifest themselves in the Bose system, we first of all discussed the possibility of Bose-Einstein condensation in the bosonic system. So we spent some time in discussing the Bose-Einstein condensation phenomena without interaction, and we concluded that Bose-Einstein condensation itself is phase transition, and this phase transition results in the formation of huge coherent state, where the Broglie wavelength becomes of the order of size of the sample, and this huge coherent condensed matter state, when the many-body state can be characterized by unique wave function, is the Bose-Einstein condensation phenomenon. So then we discussed that in addition to Bose-Einstein condensation, there is another phase transition into the superfluid state, which is related to the fact that the wave function which describes many-body coherent state of Bose system is characterized by modulus, which can be identified as an order parameter, and phase, which is responsible for superfluid properties. So existence of the vortices in superfluids and possibility for the Bose gas to flow without friction through capillaries is related to the fact that the spectrum of excitations in the systems, so excitations in these systems which we discussed are phonons, sound, and protons related to vortices are subject to Bose statistics. While the excitations electron and holes for Fermi liquid, and this what we did for Fermi system is just a pass from gas to liquid. So these excitations are subject to fermionic statistics, while the excitations in bosonic systems are bosons. So we discussed the superfluidity itself. We discussed the criteria of superfluidity. So how the superfluidity can be destroyed when the velocity of flow increases and exceeds the critical one. And then we discussed some experimentally relevant information for observation of Bose-Einstein condensation in magneto-optical traps and observation of the superfluidity phenomena in helium for quantum liquids, so to say. So both systems are entirely quantum because the statistics of Fermi and Bose systems is quantum in both cases. So this what has been done for bosonic systems, and as far as magnets are concerned, I was mostly concentrated on the theory of local magnetism. So we discussed the mean field or molecular field description of these systems, and very simply related to this mean field description to phenomenological Landau theory of magnetism. And also we discussed excitations which are magnons for ferromagnets and antiferromagnets. Actually, this part of many-body course related to magnetism was attempts to establish a connection between the theory of magnetism and phase transition theory, establish connection between microscopic and microscopic theory, and show you that fluctuations play more and more important role when the dimensionality of system is reduced. So in this course we discussed several symmetry-based aspects so we specified what kind of symmetries are violated when the transition into magnetic states occur, and we analyzed the consequences of this spontaneous symmetry breakdown. Namely, we learned that in the system of spontaneous breaking of continuous symmetry and short-range interaction, there exists a gapless mode of excitations, magnons, which is called the Stone mode. And theory which predicts distance of these Goldstone modes is known as the Goldstone theorem. And then we discuss another very important symmetry argument, which says that spontaneous breaking of continuous symmetry in systems with dimension 2 or 1 cannot lead to any long-range order except for zero temperature in two-dimensional system, and no long-range order whatsoever for one-dimensional system. As far as I said, the broken symmetry is continuous, and interaction is short-range interaction, which is a subject of Merman-Wagner theory. So magnetism theory was kind of guinea pig for us to discuss the properties of correlation functions, to discuss the origin and the way the long-range order is established in the system through increase of correlation length when we approach to the phase transition point, and discuss various visualization of magnetic systems, both in local and in principle in itinerant way. So now I have to establish connection, of course, that bosons and magnets are very much related through the bosonic character of excitations. Of course, as long as we consider two-particle excitations in Fermi system, and this is what we done considering Coulomb system, then we arrive in description of plasmons, which are also subject to Bose statistics, and so on and so forth. So you see that all the parts of the course, and I tried to make the emphasis on the excitations in the system through whole course are very closely related. Of course, the independent chapter was related to behavior of strongly correlated systems. Which actually collected many aspects of behavior of bosonic system, fermionic system, and spin systems. And in spin system, I would like to mention Conde effect, which is effect of magnetic impurities and the influence of magnetic impurities on the properties of normal metal. Again, let me make another comment relating to the magnetic and non-magnetic impurities. What did we see? That non-magnetic impurities suppress the conductivity in the system through the strict localization corrections which we discussed. However, effect of magnetic impurity is more dramatic. We saw that there is an increase of resistivity of system, which can be identified as decrease of conductivity, just due to resonance scattering of electrons with a spin field. So the mechanism of increase of resistivity for spin impurity is dramatically different from mechanism of suppression of conductivity due to elastic scattering, just because, as I said, the quantum nature of spin, namely the quantum nature of this number, is very much involved in this behavior. So we saw that Conde effect plays an important role in some physics of strongly correlated systems, and both effects of electron correlation, like strong Coulomb interaction in the system, and effects of bosonic modes in the system also play important role for description of strongly correlated systems. This is what I began with on my first lecture when I tried to introduce you a plan of our lecture, and I should say the plan is more or less fulfilled. I don't know how much you collected for your scientific luggage from this lecture. We see answer on this question during exam, I think, or at least partially. But I hope that as an introductional course to many-body physics, it actually achieved its goals. What didn't come to the course, unfortunately, is the many-body perturbation theory based on green function, because at some point I realized that in order to do it, we will need to skip one or another part of this course, which I thought is a bit more important than the methodological one. And again, studying some methods assumes that sooner or later you study the application of this method. And unfortunately, the rigorous theory of many-body perturbation theory itself requires 6 to 7 lectures, and then the commensurate amount should be spent for application, which I cannot afford in 18 or 20 lectures course. Of course, we didn't have time to study low-dimensional systems, which I try to repair a little bit in one or two bonus lectures. Of course, this course didn't touch at all the subject of phonons, because I assumed that physics of phonons has been studied in the course of solid-state physics when we discussed at least of monatomic and diatomic one-dimensional lattices, and also learned about acoustic and optic mode of phonons. Of course, I did not study in this course of many-body physics any kind of time-binding models of Bloch functions, which are single particle approximations. So I try to concentrate on many-body effects manifest themselves in coherent or cooperative phenomena, and I didn't have time for detailed refreshment of the phase transition theory, which I believe is probably not sufficient. Well, let's see what we discussed as an example. What your understanding of the phase transition theory will come clear when I see your homework and when I see your answers on exam. Okay, so that's probably all for summary. I think I did not miss anything. And before I put the last point in all the story, I would like to say a few words about exam once again. So don't be afraid for that. It's not a way to, I don't know, punish you, so to say. Well, exam has two sides. First of all, it is for you to understand what you understand better and what you understood not as good as that, and probably develop some program for yourself what to learn more and what to study more. And this is also a test for myself, because I need to see which of my explanations were simple and transparent, and which of them were not at all simple and transparent. So, as I said, I'm not in a position to be very strict with your grades and so on and so forth. This is for you. It's you who are learning these things, and this is your responsibility to get as good knowledge as it is possible. And I'm here just to help you with that. So therefore, I appreciate it during the course, and I still appreciate it all the time, your questions which you ask, because asking questions means learning as well. When you ask questions first yourself, and then your colleague, and then your supervisor or your lecturer, you try to formulate what is not clear for you, for yourself, and try by formulating the question. In many cases, you already formulate a part of answer on it. So you are going to do your career in physics, and you are going to study some branches or some fields of theoretical physics. Therefore, what I also wanted to tell you is that you need to come to self-education. If you don't understand something, of course, you are welcome to come to me, you're welcome to come to my colleague, you're welcome to discuss it between yourself, But it's also a good idea to go to library, to take a book, to fill the gap in your knowledge in quantum mechanics and statistical physics, and to work on it. It is never a bad idea. So more and more you try to understand yourself. More and more you're trying to formulate it in different terms and explain it to somebody else. More leads to more understanding of the subject. So try to work yourself. Try to ask yourself some questions. Try to find out the answer to such questions. And this is in most of cases how research works. So at some moment, sooner or later, you will understand that you don't feel yourself happy with some theories, with some explanations, with some arguments, and you try to elaborate your own arguments. And this is already the time you start your own independent research. So try to all the time learn something, try to be critical, and do not take anything for granted just because your friend or supervisor or somebody else said, try to see it in a critical angle, try to reformulate it and address it in a different way, and this is more than halfway to your independent research. Okay, that's all for today. Wish you good luck with the homework and exam. You are, as I said, all the time welcome to come and ask me. I will be absent next 2 weeks, but then I come. Meantime, we will have tutorials. Tutorials will fill in some gap in what we didn't have time to discuss. But of course, most of education you will get it from yourself, from reading books, from reading papers. And the fifth motivation, the fifth goal of my course was also to provide a background to read books, to understand what is written in books, and eventually to read papers and understand what people are writing in nowadays. Okay. Questions? If not, thank you very much.
just want to finish saying something about conjugation, conjugacy classes in the symmetric group, and then quickly tell you about the Syllo theorem,